This is a question on electrode potentials. There are 4 sections to it, A through to D. Have a go at each of them and then see how you've done. So here's parts A and B, part C, and finally part D. So if we go back to the answers and we take a look, for part A, we want to know which of the species is the best oxidizing agent. Now, you will find a really quick way of spotting this, but I'm going to go the long way round so that we understand precisely why the answer is what it is. The first thing when we're talking about best or worst is we're going to go to the extremes, the most positive or the most negative. And on here, it is actually in order. Bear in mind, they aren't always, so do be wary. Now, if I then build a number line with those two, the number line will always go in order of most negative to most positive. So the most negative goes on the left, the most positive on the right. And when we draw the number line out, we always know that the electrons will flow from left to right. They'll always flow from the more negative to the more positive. Now, for that reason, we know that whatever's happening on the right-hand side will be reduction. And we know it's reduction because electrons are being gained. But the equation on the left will always be reversed from the half equation that you've been given. It will always be reversed to the oxidation half equation. So in this particular example, it would actually be Fe goes to Fe plus 2E minus if it came to combining those. Now from there, we can recognise that if something is an oxidising agent, it's reduced. And I can see that in the top of this table, I have got Cl2 that can be reduced. And it will be reduced, and it will act as an oxidising agent to Fe. But more than that, if I combined that top half equation with any of the other half equations, it would always be on the right-hand side, which means it would always be reduction, which means chlorine is always the oxidising agent. And it's that reason that we can be confident that chlorine is the best oxidising agent. Then we have to write the conventional representation for the cell used to measure the standard electrode potential for the conversion of tin 2 ions to tin. Now I'm going to start with the standard hydrogen electrode, and you have got to know this. It's H plus ions, H2 gas, and a platinum electrode. And there is a phase boundary between each of them, so it's a single solid vertical line. And it's important to note that when you do the standard hydrogen electrode, irrespective of the values, which is what determines the number line, we will always put the standard hydrogen electrode on the left-hand side. From there, we need to add a salt bridge. We represent that with a double vertical solid line. And then we've got to add our tin and tin 2 plus half cell. Now you'll notice I've put the Sn plus 2 next to the salt bridge. It will always be that the higher oxidation state goes closer to the salt bridge. But there's another way of recognising that in this circumstance, because we have got, if you consider the half cell, a tin electrode dipped into tin ions in a solution, and it's those ions that touch the salt bridge. So there's a logic to it. You'll actually get 2 marks here. 1 for getting the order correctly and putting everything in the right place, and 1 for having all of the species present. We move on to part C. Calculating the EMF of a cell. Now, let's take a look, based on what's written down, which 2 half equations are we interested in? Well, it's going to be the Ag plus to Ag and the Sn2 plus to Sn. Both of those are reduction, which can't be the case. So we're going to find out which is oxidised and which is reduced. I'm going to draw my number line. I put my 2 things on. I go from most negative to most positive, and I write my half cells on top. Because I've drawn it correctly, because I've got the most negative on the left and the most positive on the right, my electrons will flow from left to right, from the more negative to the more positive. Now, in terms of working out the EMF, it's simply the difference. Alternative name for voltage is potential difference. So it's the difference between the two values. To get from negative 0.14 on the number line to 0.8, you're going up by 0.94 volts. But for the half equation, we're going to go back to that number line because it is so important. Whatever is on your number line on the left-hand side, we will reverse the half equation that's been provided. It will always be the reduction half equation on the right-hand side, but we need the oxidation half equation on the left-hand side. So I am going to take my Sn plus 2 2e minus goes to Sn, and I'm going to reverse it. Moving on to part D. And on this, we want an equation for the reaction of silver 1 ions with iron 2. I've started my number line, you can see where this is going. But I've also done a little asterisk here next to the Ag+. That's actually the only place that Ag+ exists here. Now, if that's reacting with Fe plus 2 ions, those Fe2 plus ions have got to be on the other side of their half equation. Because otherwise, it would be Ag+ reducing and Fe2 reducing, and there has to be one reduction and one oxidation. So I'm going to use Fe3 goes to Fe2. Once I have them, I substitute the figures into the number line. I've got my iron half equation, my iron half cell on the left, my silver half cell on the right, and because that means that electrons are going to flow from left to right, that means that there's going to be a loss of electrons in the iron half cell. So we're going to swap that equation around. We're going to reverse it. We always reverse the one on the left. Now the next thing I've got to do is combine those half equations. To do that, I've got to make sure the electrons are balanced. And in this case, I have an electron on the left and an electron on the right after reversal. So I don't need to do any multiplication of half cells, and that allows me to build this equation.